f of x. So we get f prime of x. This is negative 6x squared plus 2 over 2 the square root of x, which will be simplified, minus, but plus 4 over x squared. So this is it. So this is negative 6x squared plus 1 over the square root of x plus 4 over x squared, and this is it. Any questions on number 1? Now on g prime, the numerator prime is 3. So I have 3 minus 5x minus the numerator times the denominator prime, which is negative 5, over the denominator, which has to be squared. Now I distribute, so I get 9 minus 15x, but then I have plus 15x, and 3 negatives will make a negative. These two go away. 9 minus 5 is 4. Any questions on these problems? I'm pushing my computer further. Any questions on these? Okay, so I'm going to share my screen and look at problems from section 3.3 on derivatives of trig functions right here. So let's see what we would like to choose from here. So we have differentiate from 1 through 22. Anything you'd like to pick? They're all combinations of different trig functions or just trig functions with other functions. What catches your eye?
Can we try 6?
Which one?
Number 6.
Number 6. Let's start with number 6. So number 6 is g of x equals 3x plus x squared times cosine x. Perfect pick. So now let's take a look. When we differentiate something like this, 3x prime, can anyone give us 3x prime?
3.
Yes, very good. Plus. Now here we have to identify that we need to apply which rule?
Multiplication.
Yes. So product rule requires us to differentiate the first function. What do we get?
2x
times the second function plus the first function times the second function prime. I know this is new. Cosine prime is negative sine x. Yes, I will distribute. I mean, I will, this is not a distributive law, but I will remove parentheses, multiplying positive by negative. So I get 3 plus 2x cosine x minus x squared sine x. And this is it. Any questions on this before we look at something else?
Would or should we move the like plus 3 to the very end, or does that not matter?
Say that again.
The 3 plus at the beginning.
You can rearrange it the way you like. It really is not important, but yes, you can. So let's say negative x squared sine x plus 2x cosine x plus 3. You can, if you want to say, okay, I want to arrange everything based on x squared. It's not important because this is not a polynomial.
Okay.
So if you keep it in this form or this form, they're both okay. Perfect. Back to the book. Let's see if we want to look at anything else. I will choose 19. If you feel like choosing something else, let me know. For now, 19. And 19 is y equals t sine t over 1 plus t. Which rule applies here?
Quotient.
Yes, quotient
And
indeed.
product.
And
right?
product. Very good. Awesome. Both. Great job. So y prime will be this squared. So now, the top function prime, let's write it like this first. First, top function prime times the bottom one minus the top times the denominator prime. Can anyone give us the denominator prime so I can put it here?
Is that just 1?
Exactly. So I have nothing to put in. Awesome. So now, only now I will deal with this. So remember that there must be a 1 plus t and the minus t sine t over 1 plus t everything squared. So we use the product rule now. How much is t prime?
1.
Very good. So we have sine t plus t, the first function, times sine prime. But sine prime, I know we only discussed this today, is cosine. I have to continue distributing. I have 2 terms here and 2 terms here. I have to multiply. 1 distributed to these 2 and t distributed to these 2. So sine t plus t cosine t plus t sine t plus t squared cosine t minus t sine t over 1 plus t everything squared. Yes. And I'm happy that at least 2 terms go away. And there is nothing else. I will rewrite it and leave it alone. Sine t plus t cosine t plus t squared cosine t over 1 plus t everything squared. And this is it. That's good enough. Any questions on number 19? Anyone? Any questions on number 19? Everything okay? Okay. Do we feel like looking at anything else? Because of course we are getting to 27 through 30. Find an equation of the tangent line to the curve of the given point. This is the same theme over and over, and over. So, can anyone choose 27 through 30? We are given a function, we are given a point, we are asked to find the equation of the tangent line to the curve at the given point, and later on you will see that this equation approximates the function near x that is given to us. Okay, any preference? Any preference?
We tried 27.
Which one you said?
27.
27, very good. So 27, we have y equals sine x plus cosine x. The point given is 0, 1. I always like to look at x equals 0. Yes, this is 0, this is 1, so y is 1. Check. So we know that we have y minus 1 equals the slope times x minus 0. x1, y1. So I need to determine the slope. How do I determine the slope of the tangent line to the graph of y at 0, 1? How do I determine the slope?
Differentiate.
Yes, and then plug in what? So this slope will be f prime of 0. This is it. F prime of that x value. Can anyone give us y prime or f prime? Sine x plus cosine x. Sine x prime is cosine x,
Cosine
but minus.
minus sine x.
Very good. Awesome. Now we want to evaluate this at 0. At 0, this is 1 and this is 0. So y prime f prime of 0 or y prime, I don't like y prime when x is 0, is 1. Because I have to write this vertical line and put x equals 0. But we have to use it. So it's 1. So I have to go back and rewrite the equation. Stop me, please, please, if you have questions, please, anytime. You know that already. So my 1 minus 1 equals x, or y equals x plus 1. Because this is 1. So 1 times x is x, y minus 1 is x because this is 0. So then we add or remove negative 1 to the other side. And we get the equation of the tangent line to the graph of the given function at this point. This is the line that can approximate this function very well near 0. Not at 1. When we say near 0, if this is 0, we mean here. 0.1 minus 0.1, 0.2 minus 0.2, pretty much. Further away, we need a different equation or a different tangent. Good, very good. Is this okay? Do we need to work on other problems? Because I still have something to present. This is not done. Of course, do not ever, I didn't present this yet, this is our next step. So this is what we have to look at, but first I have to explain these limits. So don't ever discard limits and say, oh, finally I'm done with limits. You will never be done with limits. Not in Calc 1, not in Calc 2, and not later. So that's why they're so important. Okay, so I'm going to stop sharing and discuss something very important. Do you remember that we said that there are 7 indeterminate cases? And we looked at 3 and 4 more. Not yet, not in this chapter. Do you remember what those 3 were? So let's review those 3 cases that we encountered in limits, of course. For limits,
Infinity
right?
over infinity.
It will be 0 over 0 was the first one we discussed. Very good. Infinity over infinity, that was the second one we discussed. And what was the third one?
Wasn't it when one side didn't match the other?
So these are the 3 indeterminate cases that we looked at. 0 over 0, infinity over infinity, and infinity minus infinity. Why are they called indeterminate? Because the answer, at least initially, is no clue. No prediction. Have no idea. But hope. No clue where it's leading us, but there is hope. Versus, what is the one with no hope? Let's review that. Can anyone tell us what is the one with absolutely never hope?
It's a positive number over like
Any
Zero.
number, any number
any
over
number
0.
over 0.
Exactly. So this could be anything, but of course not 0. But not 0. So if it's a number, positive or negative, we don't care, over 0, this has absolutely no hope. And what are the answers? Possible answers for no hope?
Infinity, negative infinity, or D&E.
Excellent. Excellent. Thank you so much. Great job. So now I am going to discuss these 2 because I want to present a theorem that only works in these 2 situations. And I know your students always ask me, what about L'Hopital's rule? What about L'Hopital's rule? Yes, this is in chapter 4, but I will not wait till chapter 4. I will present it now. L'Hopital's rule, that's his name, L'Hopital's rule. This mathematician said this. Number one, if it's a limit. Number two, if you get initially 0 over 0 or infinity over infinity, these are the hypotheses. Both have to be fulfilled. So first of all, if I don't have a limit, I cannot use L'Hopital's rule. If I don't get the initial evaluation or initial setup, if you want, either this or this, I cannot use L'Hopital's rule. Both conditions have to be fulfilled. Assuming they are both fulfilled, he showed then the limit Sx approaches a from f of x divided by g of x, a function over a function that initially gives us 0 over 0 or infinity over infinity, can be determined like this. Notice that we are not applying the quotient rule. This is something specific if these two conditions are fulfilled. So it's a specific situation in which both the limit and this function, this ratio, gives us, or both give us this initial assessment. Then we are not using the quotient rule. He showed that this limit can be determined as simply differentiating the top and differentiating the denominator. If I have the initial assessment this, or any other of the four, I cannot use L'Hopital's rule. However, those situations, these four and this one, may be changed, we're going to get to that in chapter 4, into these two. If we can change them into these two, and we do have a limit, then we can continue in the same way. Okay, perfect. So what am I saying here? Because I would like to talk about, that's my page 6, the next step. So we have limit as x approaches 0 from sine x over x, or limit as x approaches 0 from x over sine x. This specifically is a very important function. So let's determine those limits. What do we need to do first? We're asked to find the limit, and we have to do something first. What?
Plug in the final.
Yes. So plug in 0. When I plug in 0, what do I get? When I plug in 0, what do I get?
0 over 0.
Yes.
0.
So there is hope. Furthermore, there is a limit. There is a function. And the initial assessment is 0 over 0. I can use L'Hopital's rule. I can apply L'Hopital's rule. Can anyone give us a derivative of sine?
Cosine.
Very good. Can anyone give us the derivative of x?
1.
And now plug it in and give me the answer. We are applying the limit operator, so we can write the final answer now.
It should be 1.
It should be 1. I'll come back to this. This is a very important result. Let's also do this one. So, when x approaches 0, the top goes to
0.
yes.
Zero.
The denominator goes to
0.
perfect. I have a limit, I have a function, and I have the initial value, the initial assessment 0 over 0. All conditions are fulfilled for L'Hopital's rule. So therefore, limit x approaches 0. Please differentiate x.
1.
Please differentiate sine.
Cosine x.
Please apply the limit.
That would be 1.
Excellent. So now, what I would like us to look at is this limit. Allow me to